Right. So, for our course selected topics in decision modeling, today we are in our 25th lecture. So, if you recall, we were discussing non-linear programming, right. So, today we are going to discuss the numerical methods for unconstrained NLP. So, the numerical methods for unconstrained NLP, you have seen that there are several methods in which we actually solve nonlinear programming problems. Let us see where the numerical methods actually come in. So, if we have let us say a single variable unconstrained nonlinear programming problem, say we have a single variable differentiable function f x, and to find out the global optimal solution x equal to x star, we have the necessary and sufficient conditions. So, we take the first derivative, put it equal to 0 at the given point, that is the optimal point, but that alone is not sufficient, that is necessary condition. The additional constraint that we have to check for sufficiency is whether the second derivative value is, if it is less than 0, that is for maximization, and greater than 0 for minimization. So, this is a simple thing that we have already seen. Then sometime if the second derivative is difficult to obtain, and also the first derivative is available, but not easy to solve, then we have a method called the bisection method, and we have discussed it. That method basically meant that we take two values x underlined and x bar, and they should be between two extremes, so that the extreme point lies in between. That you have to ensure that these are the two extreme points, one on one side and the other on the other side. Then through the method of bisection, and by evaluating the gradient and really noting whether the gradient is on one side or the other, based on which we keep the averaging those two values and looking at which side it is on, and then reducing the search space, and finally obtaining the extreme point. So, that was the bisection method. But moment we had multivariable, then it is not easy to obtain the first or second differential. That time we had two more concepts we have introduced, that was the concept of gradient and the concept of Hessian matrix. The concept of gradient is actually, these are all first order partial derivatives. We equate them to 0 at the x star, which is our maximum or minimum, that is an extreme point. But then additional the sufficient condition is that the second order partial derivative, that is the Hessian matrix, that matrix should be positive definite for the relative minimum and negative definite for relative maximum. Is it all right? So, when we take that Hessian matrix and we find the eigenvalues, they will actually determine the the positive definiteness or the negative definiteness of the matrix. So, this far we have already seen. Now, there was another very important method, that was the gradient search procedure. There the real advantage is that we really do not need the second, that is the Hessian matrix, to be computed. So, if we know the concavity or convexity of the the function, as the case may be, concavity for maximization, then we take the iterative step, that x dash equal to x dash plus t star, the gradient of the function at the given point, and keep finding that starting from a point x, I mean trial solution x dash, move towards the gradient. The essential idea is that if we are having a maximization problem, then as you move on, the gradient should go up, right. With increasing gradient, that means the increasing function value move towards the extreme point and keep modifying your trial solution till you reach almost at the extreme point. So, that was the gradient search procedure, is all right. Now, sometimes we have what is known as the numerical methods also. So, supposing we equate the f dash x, that is the first order derivative, to 0, but then it may not be easy to solve that particular resulting equation, because it may be having higher order terms, right. So, what we can do, we can make use of numerical methods. So, in this particular lecture, we are going to discuss two such methods, the Newton's method and the Regula-Falsi, right. Once again, why do we need these numerical methods? These numerical methods are required to solve unconstrained nonlinear programming problems, particularly when we equate the gradient to 0, but then the resulting equation is of higher order, and we need to, it is difficult to solve directly. So, let us see the procedure. So, really the procedure is like this, that we consider the first derivative of the function, that is f dash x as a straight line at a given point x k, and then obtain the next point at x k plus 1, where k is the current iteration. So, what we need to do? We need to find out the first derivative and we need to find out the second derivative at that given point. Is it all right? So, we take a trial point x dash k and then find out the first derivative and the second derivative, and these two are helping us to iterate from a given point to the next point. So, that is the Newton method, and then we have x k plus 1 value, and x k plus 1 equal to x k minus f dash k x k by f double dash x dash k, where f dash x is our first derivative and f double dash x is the second derivative, right. So, that is the process, iterative procedure. And what we should ensure, we really should ensure that the function value is really decreasing if we are finding a minima, and function value is increasing if we are finding a maxima. So, it may so happen that if it is not happening, obviously the process has come to a point where it is not helping anymore, right. So, that is the Newton's method. Now, let us see an example, or before that let us look at the how exactly it is happening. So, supposing we plot f dash x. So, this side is x and this side is the function. So, see, this side is our x and this side is our function, that is f dash x, right. So, let us say this is our plot. Now, assuming just arbitrarily, so that let us say this is where our x star, that is the optimal point, lies. So, what happens, if I take a given point, say what is this point? This point is our x k, that is our trial point. So, actually this is our x k value at this point, because this side is x. So, this is our x k value. Now, if I take the gradient, tangent of this f dash x and then take the slope, that is nothing but f double dash x k, is it not? Because that is the second derivative, because this line is first derivative f dash x, and if we take a slope at a given point x k, obviously that should be our second derivative. So, that is the equation written here, that is f double dash x k is f dash x k by x k minus x k plus 1, you know. So, this is our new point x k plus 1. So, this side is, you know, what is this value x k minus x k plus 1, and this side is our f dash, because this is our f dash value. At this point this much is our f dash x k value, that is the functional value. So, this is can be the way by which we can define the f double dash x k. So, a little manipulation, you know, you can find out that x k plus 1, because x k minus x k plus 1, take it that side, is f dash x k by f double dash x k, and then just rearrange the terms, then we get the new iteration value is the old iteration value minus first derivative by second derivative at that point. Is it all right? So, I hope you understood the method, how exactly this Newton's method really works. So, if you have understood the method, then let us go ahead and solve a problem, and then see how exactly it works. So, here is our problem, that solve numerically the optimal point. Suppose you have maximize f x 12 x minus 3 x to the power 4 minus 2 x to the power 6. So, at a given point, if I take the derivatives, that is the first derivative and the second derivative, what will be our first derivative? The first derivative will be, you know, equal to f dash x, if you take then 12 x, it should be 12 minus 3 x to the power 4. So, 12 x to cube 2 x 6 minus 12 x to the power 5. Is it all right? So, the same thing is written here, 12 into 1 minus x cube minus x 5. So, if this is our first derivative, what will be our second derivative? Look here, minus 12 x cube, so minus 36 x square and minus 60 x to the power 4. All right. So, that is how we have found out the first derivative and the second derivative. Now, to satisfy the necessary condition, we have to put f dash x equal to 0, right. So, that should be our extreme point. Now, the question is that this particular value is not easy to find out. What should be the value of x at this point, because we have put equal to 0. So, finding the value of x is difficult analytically. So, that is where we are trying to find out through Newton's method and the numerical method. Not only that, we have to ensure, see one thing is ensured already, that this one is a negative quantity. Can you see that whatever be the value of x, the x square and x to the power 4, they are positive. So, since we have minus 36 x square minus 60 x to the power 4, so this has to be a negative quantity. So, since the second derivative is negative, that actually ensures the concavity of the curve. That means, we have an extreme point which is a maxima. All right. So, that we have already ensured. So, after we have ensured that, now the question is that what is the value of x if I put f dash x equal to 0? That is our real challenge now. Now, let us see how it actually happens. So, what we do, we find the first derivative at this point, which is 12 into 1 minus x 1 cube minus x 1 to the power 5. So, it comes to minus 12, right. And what is f double dash x 1? So, it will be minus 96 for a given point. See, we started an arbitrary point x 1 equal to 1, right. So, suppose we arbitrarily start at a given point. Now, for that particular point, the f x value is 7. Now, question is, why do we start with 1? Because first of all we see that by putting 1 we at least get a positive value, and if we by looking at the nature of the function, if I would have put 2, obviously the value would have been negative. So, you have to have a good starting point, that is an important thing to begin with. Now, we find the first derivative and we find the second derivative, and then we can iterate and find out the next value of x 2, which comes to 1 minus the f dash x by f double dash x. So, that is equal to 1 minus 12 by minus 96. So, 1 minus 1 by 8 equal to 7 by 8, right. So, that is what you get, and which is 0.875. So, this is our next iteration. Look here, if you put 0.875, then our f x value comes to 7.844, right, slightly better value is obtained. So, from a value of f x equal to 7, we have now come to 7.844. So, that leaves us for our next iteration. So, again we move ahead. Now, this time we have taken our next value x 2 is 0.875. If you recall, our functional value was 7.844. So, again if we actually obtain at this point the first derivative and the second derivative, the first derivative comes to minus 2.194 and second derivative comes to minus 62.733 by putting the x 2 value. So, again by the similar computation x 3 comes to 0.840, right. So, that is our next iteration value, and what is the functional value here? That becomes 7.884, right. So, from 7.844 we have improved it further to 7.884. Let us move further at the next iteration. Now, we have used what is known as an Excel sheet, and what we did, we actually put those values and use that same iteratively similar calculations. We just copied number of times. The x obtained from the first becomes the x for the second, and x for the second becomes x for the third. That for the third, whatever comes out at the end goes for the fourth, like this. So, that is how it progresses. So, initially we start with a value of 1, then 0.875, then 0.84, up to this point we have seen, and then further if you go we get 0.83764, and subsequent look at the f dash x value. So, it starts from minus 12 to minus 2.19 something, minus 0.13 and finally minus 0.000. So, you see with subsequent iteration the first derivative is nearing a 0 value, is all right. So, x is also slowly merging to a given value. So, maybe after these many iterations probably we can say that for this value, that is 0.83763, probably is a good approximation for the f x value of 7.883946. You can iterate further, but we have to see whether we are really improving, is all right. So, that is the Newton's method. To have a review of what exactly we have done, let us take another problem and quickly see. So, supposing we have to solve numerically by Newton's method, maximize f x equal to 1 by 4 x to the power 4 plus x square minus 4 x. Again take the first derivative and the second derivative. So, the first derivative f dash x equal to df dx is x cube plus 2 x minus 4, and the second derivative becomes 3 x square plus 2. So, that was the first and the second derivative, and after obtaining that, the necessary condition, the first derivative should be equal to 0, that is the necessary condition. So, again it is difficult to solve it. So, we follow what is known as a numerical method. So, what is that numerical method? Once again let us see that by Newton's method. In the first iteration, what we do, we evaluate the f dash x. Let us say again we start with a value of 1 and f x is minus 2.75, and here this was the minimization function. So, we find that the new value of x 2 comes out to be 1.2, right, and functional value from minus 2.75 goes down to minus 2.8416. All right. That is the first iteration. Then subsequently, using this value, we move to the second iteration, and again we compute the first derivative and the second derivative, and when we take the ratio, then we get 1.1797, and the functional value move down from minus 2.8416 to minus 2.84391. Okay. So, that is the second, and again using Excel we have tabulated the value moves from 1 to 1 to 1.2, 1.1797 and 1.1795 is all right. So, at that level, look at the f dash x value is almost 0, right, nearly almost 0. So, that is how we find our optimal solution, that is x star equal to 1.1797 and f x star equal to minus 2.84291 is all right. So, this is a kind of method through which we can find out the functional value, the extreme value by a method of iteration. Now, see the other method which is known as the Regula-Falsi method. So, again this is another method where the f dash x, the first derivative, is considered as a straight line, is all right, it is as a straight line, and the interpolation is made use of to find the value of x at for f dash x equal to 0. The advantage is there is no need to calculate the second derivative, right, but then we need to have two starting point a and b such that the f dash a is negative and f dash b should be positive. So, see there is a function f dash x, for a value of a the value is negative, for value of b f dash x is positive. So, obviously, f dash equal to 0 should be somewhere in between, so that we can interpolate between them. So, this is the interpolation equation that we have, that x equal to b minus f dash b, b minus a, f dash b minus f dash a, right. So, if you do a little bit of manipulation, it will be like this, x equal to f dash b minus f dash a, and on top what you have, b into f dash b, that is the first term, minus b into f dash a, that is the second term, and then if you again see here, then the first term is b into f dash b, and the second term is, I am writing it here, plus a into f dash b, all right. So, look here, these b f dash b and b f dash b, they cut each other. So, what is remaining? A into f dash b minus b into f dash a by f dash b minus f dash a. So, if I put it here, that is how we get that from the interpolation equation, we have been able to find an expression, that is x equal to a f dash b minus b f dash a by f dash b minus f dash a. So, it is nothing, you just calculate this, you will get here, is all right. So, now the question is that resulting x, that is the iterative value, you compute and then see whether it is negative or positive. If it is a negative value, then replace the x a by x, because a is the negative. So, a should be now replaced by x. So, it is like this. So, suppose there is a line, suppose this value is 0, this is a and this is b, a is negative, b is positive, all right. Now, what happens, suppose we get x here. So, if we get x here, now x will become a. So, this will become a. So, this is our new a, but on the contrary, suppose this is a and this is b and we get x here, then x will be our new b, is it all right. So, now the iteration should be here, or in this case it should be here. So, like this, with every subsequent iteration you are nearing the point, that is the 0 point which you are trying to find out. So, that is the iterative method in the Regula-Falsi. Fine. So, now that we know what it is, let us see an example. So, let us take an example that f dash x equal to x cube minus 2 x minus 5 equal to 0. So, we take 2 points 2 and 3 arbitrarily, knowing that if I put 2, we get 2 to the power 3 is 8 minus 4 minus 5. So, we know f dash 2 equal to minus 1, and if I put 3, then x 3 to the power 3 is 27 minus 6 minus 5. So, we get f dash 3 equal to 16. So, one is negative and the other is positive. So, we have one value on negative side, another value on the positive side, and then we iterate. What is the iteration step? X 1 is a f dash b minus b f dash a by f dash b minus f dash a. So, we already found f dash 2 and f dash 3. So, 2 into this minus 3 into this, and please note that the function itself is f dash x. So, there is no need to differentiation, because that was the function itself, right. So, we find equal to 2.058, and the new value for the function f dash 2.058 is a negative number. So, since as I say in the scale, this side is somewhere in between. So, this is negative, this is positive, this is a, this is b. So, we get an x which is negative. So, that means now this should be our new a, fine, that should be our new a. So, what is our new a going to be? It should be 2.058, right. So, then we should iterate between 2.058 and 3, right. So, again we do that. So, again same thing, we find f dash 2.058 which is again negative and f dash 3 is positive. So, we find again through that at the next iteration we find the x 2 value is 2.081, and when you put that we find another negative value. So, that should be our new a, is it all right. So, once again we followed, this is nothing but the second iteration, and at the second iteration by following similar procedure we found a is 2.081 and b equal to 3. Let us move further. At the next iteration again we put 2.081, we find minus 0.1501 and that equal to 16, and again the computation shows 2.089. So, the new value is minus 0.06177. So, that is what we get after 3 iterations, the x equal to 2.089 and f dash x equal to minus 0.06177. Is it all right? So, that is how the Regula-Falsi method calculates the f dash x equal to 0, it solves and finds the optimal point. Is it all right? So, we have seen the numerical methods for unconstrained optimization in this particular lecture, right. So, thank you very much.